Great. Hey guys, thank you so much for being here. I hear the traffic today was horrible on 237, 101. You guys came from Redwood City, so so thank you for everybody who made the trek. I know some of you came from San Francisco. Thanks for being here. And just want to welcome you all. My name is Charu Madan and I work at DataTorrent, and I'm one of the organizers for this meetup. That's kind of my evening job. I have another day job, but this is what I do after 6 p.m. or whatever. And it's a pleasure to have Dev from PubMatic here to give a little bit of an overview about their journey with us and their working with us as a product. And then we have Thomas, who's our lead architect from DataTorrent, who will talk a little bit more about Apex, our architecture, give you a little bit more of a technical deep dive on the product itself. I'm just curious, as a show of hands, how many of you have heard of DataTorrent or Apex or one or the other? I mean, I would love to see that. Okay. And for some of you, Apex and DataTorrent is new? Yeah. So just to tell you a little bit about us as a company, we've been around, DataTorrent has been around since 2012, and what's new in our sort of history is Project Apex, which is something we just recently open sourced Project Apex, but as a company we've been around for about 3 years. And Project Apex came into being, we announced it in June. The code was released in end July. On August 12th, we basically proposed this to be an Apache project, and on August 17th, we were, Apache incubating project. So it's been as Project Apex, it's been a relatively short amount of time, but we're really very encouraged that we have a lot of traction and a lot of good response. So, and a part of this, meetup and developing this community is all about being a part of the Apache open source. The PubMatic guys have been with us in this journey for actually longer, and that's why it's really delightful and wonderful to have Dev here, who's been with us. Dev, you've been on the project since pretty much the beginning, right? Yeah. So he's going to give you more in-depth view of their use case, their usage, what they do as a business, and what kind of problems our product Apex and solve for them. And Dev, over to you, and stage is all yours, so I'll let you get started.
Hi guys, am I audible to the back? Okay. Okay, you need to start this. Doesn't seem to work.
No, I think you just have to open this. Let's see if that works.
All right.
Yeah, there we are.
Just a quick show of hands, how many of you are familiar with the ad tech domain? Okay. Right, so few, so I can lie to a certain degree and people wouldn't figure out. Anyway. All right, so just a brief introduction of what PubMatic does. So PubMatic is an ad tech company per se. We focus on digital ad serving, and the real focus of PubMatic is sort of shifted from being an SSP to being a marketing automation software company. What that means is that we are working closely with the demand side as well as buyers to really help publishers monetize and realize their digital assets. In simple terms, you go onto a page, let's say you go into the eBay site, and you go into one of the remnant pages, and this ad that pops out, it's more likely that we are serving that ad. And the way we serve it is that we sort of facilitate that ad being served at the best price, so eBay gets more bang for the buck, and the advertiser, let's say Nike or Adidas or Reebok, gets to deliver that ad to the target audience. So that automation or that auction facilitation is done by PubMatic. Like it said, through real-time analytics, yield management, and workflow automation, we help the publishers make smarter inventory decisions and improve revenue performance. One of the other things that PubMatic sort of pioneered was a real-time auction. So a single ad slot is being bid by several people at the same time. PubMatic runs that auction, applies a bunch of rules around it, mostly related to targeting or pricing, or to content viewability and delivery. What should be viewable, what should be shown to a particular audience or on a particular page, and then we sort of deliver that ad. Here's, for the people who are not really familiar with the ad tech as a domain, is a brief slide of how the ad tech market now works. When I say marketing automation, this is the ecosystem as we have today. So an ad marketeer is someone who wants to run a campaign or show ad. Let's say a Nike or a Pepsi or a Coke is basically an ad marketeer, and it wants to run targeted campaigns for you. Then an ad server is, it's an entity that the ad marketer interacts with to run those campaigns, actually. If that campaign wants to be run, it doesn't make sense for a single company having thousands of campaigns to go and run and execute each single one in the real world. So then came the rise of ATDs. Agency trading desks like Vivaki are basically companies that facilitate the running or enablement of campaigns in the real world. Now, that campaign needs to be targeted to a particular audience, and you also need to ensure that the right demand source for that campaign is met. That led to the rise of demand-side partners. Someone like a Turn or a MediaMath is one of the more prominent demand-side partners. So these guys make informed decisions for the ATDs, who in turn provide automation to the marketeer based on some targeting criteria and some price restrictions. They get that information from data management platforms. Now, these are the guys who basically snoop in by planting in cookies, collecting your user information, and they could be like first-party data providers, Lotame, for example, BlueKai. They provide that data to the DSPs to make an informed decision on what price to bid for a particular ad slot or for a particular campaign. Then there is the ad exchange. Now, this is where the action happens in reality. This is where an SSP brings the publisher's side of inventory and the DSP bids on it. This is like a traditional stock exchange of sorts. It's just that when you arrive at a price and all the filtering criteria or all the prerequisites are complete, you can actually serve the ad. Most famous ad exchange, DoubleClick. AOL is another one. SSP is the space where PubMatic operates in. Now, PubMatic deals directly with publishers. Now, a particular publisher may not want to show some content on his site that, let's say, doesn't suit the target audience for him. So PubMatic applies all of those rules. Then he might say that, I want this slot to be auctioned at a particular price. For example, not below $1. PubMatic does that for him. And all of a marketer creating a campaign to an ad being actually served on the page and an audience viewing it happens in about 150 milliseconds. So that's the latency of a typical ad serving use case in the real world. All right, coming to the use cases for real-time solution at PubMatic. So there are top 4 things that we were focusing on. One is real-time reporting. So before DataTorrent, we never really had a real-time offering. Everything was batched. That meant like a latency of at least a few hours before any actionable metric could be shown to the user or could be fed back into PubMatic's ad engines for any actions. Right. So real-time reporting is we identified a bunch of critical metrics around campaign monetization, which is really the bread and butter for any ad tech company. And those metrics were like revenue, impression, and click info. So the revenue is the revenue that we get after serving an ad for a particular slot. Impression is the number of events, unique events that we serve, and clicks are something that, you see an ad, you click on it, we capture that event, and there is another higher revenue associated with clicks. Essentially, they're just aggregate counters, and we also do a top-end kind of a use case. So you can actually find out what are the top campaigns running on a particular site, or what are the top 10 revenue sources or demand sources for you. For this, we are using a low latency pub sub model, which I will cover in some time on one of the next slides. The other thing that we are using, which is very critical to the business, is real-time monitoring. Now, go back. An ad marketer creates a campaign. It's being facilitated through the DSP, but I, as a SSP, have no idea how it's doing in the real world. Before we moved on to Apex, the turnaround time was 6 or 7 hours before I could get any information as to how that campaign was doing. Let's say around Thanksgiving time, which is really the peak time for any ad tech company, there are campaigns that run for a day with hundreds of thousands of dollars in spend. We wouldn't know for 6 hours of the day how that $100,000 campaign was doing. That means I'm at least losing $25,000 if I'm not doing well. With Apex, I actually know that in a few minutes. If it's not tracking well, if it's a setup issue, etc., I can go back and investigate, and I can correct that faster, so I can actually realize that $100,000 of inventory. So we set alerts around that, and we actually have a campaign and a deal health dashboard that helps us sort of monitor and watch that. Then real-time learning. We're sort of building this use case out, which is basically, so the way an auction works is that, rather in PubMatic's real-time bidding auctions, what happens is PubMatic qualifies a campaign, let's say at a couple of dollars of CPM, and all the DSPs associated may bid $2.1, $2.2, $2.5, whatever. And it's more likely that the floor that I set for my campaign may not be realized, and I just don't end up serving anything. That's where the lost bid learnings come into play. So in real time, we are actually planning to adjust the floors so we can realize these lost bids and monetize better. Basically, the idea is to have a better strike rate. Allocation engine. This is being developed in collaboration with DataTorrent team. Thomas and Tim help us out with it. This is actually the first time a feedback is going into our auction engine from DataTorrent. So we are streaming data from Kafka, aggregating, and uploading it to a data store in a fault-tolerant way. And the auction engines actually are learning both historic and real-time data to make decisions about the allocation. So this is one of the guaranteed offerings that PubMatic is developing. And for any guaranteed offering, you need some historical insights, some real-time insights to predict the frequency at which a user will visit you, and to predict the price at which you want to allocate a particular campaign or line item. Right, so just to give you a sense of the problem at hand and the scale that we operate against. So PubMatic has 6 geographically separated data centers. We run 4 of those now, and 2 are in cloud, hosted on cloud or AWS. So right now, PubMatic manages about 5 petabytes of data in its Hadoop clusters. The average inflow of data is about 22 terabytes a day, and this is auction or client info. So auction info is something that PubMatic's ad servers log themselves, and client-side info is, an ad is served, and there's a tracking call or a beacon call that's fired from your browsers, which helps PubMatic or any other ad tech company actually be certain that that ad was delivered or not, because a lot of times with ad block and stuff like that, blanks are delivered. We cannot charge the publishers for blanks. So that's the client side of the logs, and we have 3 heterogeneous data formats. One's the auction logs. Now this is zlib compressed JSON serialized data. Then we have the client logs, or which is the beacon logs that I explained, emanating from the user's browsers. These are essentially key value pairs. They have width, height, creatives, etc. Text format. Click logs. Now, when an ad is served and you click on it, you're redirected somewhere else. We capture that info because then we can charge you a higher CPM or a higher price on that click because it's more likely that you're going to do some action based on that. Now we have the average inflow of impressions that flow through the PubMatic ecosystem is about 15 billion a day. That translates to about 200K events in peak per second.
One question.
Yeah.
Why do you combine multiple data center? Why you have AWS and your colocation data?
Yeah. The reason being, right. So why do we have a combination of co-located data centers, which are geographically separated, and AWS data centers? So the co-located data centers are, so the short answer is latency. Ad serving is very sensitive to latency. If we are not able to serve an ad in 150 milliseconds, then it just times out and it goes to a passback network, so we don't realize any revenue for the publishers. That's the reason why we have co-located data centers where we host our ad servers. The ones in AWS, however, we host because we usually see lower volumes there, so we have fewer publishers in those co-located data centers, and it's in those AWS data centers, and it's not worthwhile to actually go buy some space with a vendor and host our own data center there. So, yeah.
What are you guys using as the in-memory store?
Sorry? We're using a custom store written on top of Apex. Not yet. HDHT is used for the allocation engine. Right now, for the top 3, we're using a custom store, which is a distributed hash table, but it's in memory. Yeah. Right. So this is one of our main applications that runs. So we run 2 applications, like I said, one for the allocation pieces, one for the dashboard use cases and the alerting use cases. So we are consuming data from Kafka, and we have about 64 instances of that. So we have 6 data centers. There's one in one co-located data center, DataTorrent or Apache Apex runs, and we basically pull all the raw data from the 6 Kafka clusters across data centers and get it into the centralized data center. Then, in addition to that, we have we used to have now. We used to read Avro data from S3 for a specific use case, and so the DAG looked something like at the input tier we had operators consuming from Kafka and from S3. Then we used to do some ETL, flatten it out, aggregate, and show it. So the end-to-end latency for ad serving to visualization using Kafka is about 40 seconds. And this is at 5,400 events at peak. So if you look at the trend of events for any ad tech company, what happens is in the peak hours, you get twice the volume of off-peak hours. So off-peak hours, usually the DAG that runs is underutilized. But in peak hours, consumption goes up to 5,400 events per second. We have 32 instances of the in-memory distributed store where we maintain a distributed hash table, and we use a query protocol using Kafka as a publisher subscriber in the publisher subscriber mode to query it from a dashboard. Then we have 64 instances of a dimensions aggregator. That's again a part of Malhar, I believe. And the total memory footprint of this application is 1.2 terabytes. There's also dynamic partitioning enabled for this operator. So it starts off with 4 instances and goes up to 12. Yep.
So the 5,400 events, what is the limit here?
Event is an ad request that comes in, and the auction information that we log for it.
How much data is in a typical event?
Right. So this is the size of these logs are about 1.1 K for a single event. This is more like 240, 250 bytes, and this is 90 bytes. Right. And like I mentioned, we are actually work is underway, or rather, a test application is already deployed for working with HDHT and feeding that information back into our auction engines to optimize our delivery. Right. So this is before, midterm, and where we are now. Before, we had no real-time offering. That meant that the turnaround time that we had to showcase any quantifiable insight around the 3 critical metrics that we have, revenue, impression, and clicks, was at least 5 hours. And that was on top of one of the smaller data formats that we had. The larger data format, which is this guy, auction logs, the turnaround time was like 9 hours. Right. So basically, publishers and buyers could only rely on the batch processing system. It used to use a lot of custom things. It used to run on Hadoop 1x. So we had something called a combiner. Used to take a lot of small files, concatenate them, apply block compression, and push it to Hadoop. So the turnaround time just for ingestion was like a couple of hours, and that was the earliest any data could be available for batch processing or for streaming processing. This was pre-Kafka days. So then we moved on. We went to the cloud and we partnered with DataTorrent, and we started basically reading from S3. We had a Kinesis plugin. We used to write to Kinesis, read from Kinesis, and then write to S3 and read from that S3. But this turnaround time was also 20 minutes. The good thing was, in this phase, we actually developed the S3 operators that could reliably read from any directory, or rather any bucket in S3 in a fault-tolerant way with checkpointing and make sure that there were no duplicates. And then we added dynamic partitioning to it as well. So we could start off from a couple of operators, and then we could scale it up to 20, 30, 10, depending on the load that we had. But because it was still batch writes and then reads, the end-to-end latency was 20 minutes. When I say end-to-end latency, it's the latency from the time that an impression is being served in the real world or to a user, and the time that I can actually visualize it on any kind of a dashboard. Now, where we are today, so that from that point on, we actually moved back into co-located data centers, and we started writing to Kafka and streaming from Kafka. So now we stream from Kafka, aggregate, and the results that we've achieved is the end-to-end latency has actually gone down to 40 seconds now, even at peak loads. At off-peak loads, it's just 25, 30 seconds at best. So yeah, that's under 1 minute now. This is our implementation of Apache Apex at PubMatic. So this block is PubMatic's co-located data centers. So we have a bunch of ad servers, some host serving ads in the real world. They have what we call is like auction information, or the biggest kind of logs that we do. We have written a REST proxy to write that data to Kafka. And then from a user's browser, we collect the client logs. We have a content delivery network partnering with us to batch those logs and basically write it to the proxy so we can have them in Kafka. The same model, again, flows for our AWS data centers, ad server, proxy, Kafka. And then we read all of that. So this box is our implementation of Apache Apex. And this is in one of our data centers. We don't run multiple instances of Apache Apex and then try to combine that aggregates in one place. So this is just one data center. We pull data from, there are four of these data centers and 2 of these. So we pull all of that data using a Kafka input operator, and then do some ETL on it, we have a bunch of custom rules, which we call the filter operators. And then we aggregate them, write it to a store, which is in memory. Rather, we partition it and then write it to a store. The idea of partitioning and writing to a single store is to basically support low latency queries. At these high data volumes, 15 billion impressions a day, you do not want another calc engine on top of your store to query, bring data from all the partitions, present group by, and then present a single unified view of it. So we do that using one of DataTorrent's operators and write a single row to a dimension store. So every query is essentially point to point. Now, this is something that was probably done for the first time, or at least one of the earlier iterations, which is a pub sub using Kafka. Not many people in early 2014 used to do a publisher-subscriber mechanism using Kafka. The way it works is we have a middleware dropping a custom query into a Kafka cluster. Now, we have added an operator on top of the dimension store to read that query from Kafka. Then we fire that query on the dimension store. The dimension store actually matches the right result based on the queries, on the dimensions given in the query. And it responds with the result into another operator. It constructs the response and drops it into Kafka, and the middleware reads it back. You might think these are many hops, but trust me, the end-to-end latency that this gives is about, sorry?
Which one is exactly Apex?
OK, I'll come to that. Yeah. But the end-to-end latency is just 2 milliseconds, 20 milliseconds, sorry. Evolution of the use cases. Like I mentioned, we were in Colo, reading from S3, and we had actually one view only. So you could log in as a publisher, see a bunch of things. The way DataTorrent actually helped us and Apex helped us was creating views was incredibly easy. So I could see the same data from a publisher's perspective, and I could see the same data from a buyer's perspective and from a DSP's perspective. If you recollect the slide at the start, publisher is on one end of the spectrum, on the selling side, and a DSP is on the other end, on the buying side. So they're pretty much the same things, but it's sort of complicated to get that information from multiple views. We moved from a 20-minute latency to 1 minute. And this was just about under a month's effort to cut down that time from 20 to 1 minute. We were reading Avro data from S3, and then we moved on to reading zlib from our Colo data centers. Initially, we were just reading one data type, but then we ended up reading 3, and it was just as seamless. Very easy to configure, very easy to write out those operators and assemble them. We added a filtering support with a filter chaining. So I could start off with one filter and just go on adding any number of filters, go up and down in the prioritization of filters. We also added some metadata support. So there's a task that queries for some metadata that feeds back into the filter operators for some custom rules. Right. So coming back to which operators are from Malhar and which are not. I'm sure Thomas will go into the details as well, but yeah. So the S3 reader was we inherited from Malhar, which is open source, or Apex as it's called now. So this one used to recursively read the contents of any bucket. So you give it a pattern, and you can go into a S3 bucket, and based on a partitioning scheme, it could read the contents. You could include and exclude a particular pattern of files or a particular subdirectory or a sub-bucket. We were actually able to externalize the schema for reading different kinds of Avro files. We implemented file state management on top of the base operators in Malhar. This was done to make sure that we don't really read the same files over and over again, because duplicating data is never really a good thing, and it gives us a wrong picture of what's going on in the real world. Fault tolerance, right? So we actually built in a few things that enable us to exactly start reading a file. If for example, if I'm reading a file, I read 1,000 records, and my operator goes down. We had added fault tolerance in a way by way of checkpointing using the RTS framework to to exactly read from 1001 event and not really read those 1000 again and the rest. This is, again, native to RTS. Ability to look back at skipped files. This is a custom implementation done by us. We maintain a cache and we maintain a record of the files. And then we could go back a couple of directories even after we have moved on. If a file was written after we sort of read that directory. The throughput that these operators used to give was about 12,000 reads a second, with 1.2 KB was the size of an event then. The other operator that we inherit from Malhar or Apache Apex now is the Kafka input operator. So we can actually consume from multiple Kafka clusters across DCs, and some of our data centers have more than one Kafka cluster. So it's not just different data center. It's one data center, multiple Kafka clusters as well. We have an offset management support. Again, this is given out of the box from Malhar. And this enables us to start reading from a particular point of consumption in Kafka and also checkpoint what we have read. The reads are fault tolerant, provided natively by RTS. Idempotency and exactly one semantics are also supported out of the box. This was something that we added along the way with the DataTorrent team, which was controlling the reads that you do. The reason being, a lot of times, the downstream operators in your DAG are not able to keep up with the upstream operators. Now, Kafka input operator is a very lightweight operator. Its only job is to read from Kafka and move all of that data to the next operator. The ETL operator, however, is an operator that typically would do decompression if your data is compressed, and deserialization, and then flatten it out. So those operators tend to be heavier on CPU, and it's very likely that a failure there could result in one of the upstream operators failing as well, because you eventually run out of buffer server memory. These are sort of custom operators developed. Dimension store is so this is actually in production. 32 instances of this at 5 gigs each run, 5.5 gigs each run. We have a distributed memory store. It has a distributed hash table in it, partitioned by views and then by the different dimension combinations that we have. So a dimension combination falling into a particular view would be a single entry. So I have one publisher and one site, and it falls into, let's say, the publisher view. That becomes a single row in one of the many 32 instances of this operator that we have. So dimension store essentially is like the sink for all the aggregations that we do. So the heterogeneous log types that we have, we flatten it out into a single format. We aggregate it, and those aggregates are actually joined and merged into a single store. So the clicks, the impressions, and the ad serving events or the auction logs all go into a single row in the dimension store, depending on the uniqueness, obviously. So we support point-to-point querying since we do an aggregate of aggregates. So the aggregates essentially arrive out of order, and then those become individual tuples in the aggregate operators. But when they go to the store, we run an aggregate of aggregates. So everything is combined, and a single unified view is given. HDHT is something that we are working with currently for the allocation engine. Again, it's a HDFS-backed key value store. It's fault tolerance, supports random read and writes. It actually gives, DataTorrent actually gives an out-of-the-box support for visualizing the events inside of the store. So that helps us debug even before any event reaches the UI. So I can actually set an alert on a particular combination to see how it's tracking through our system. Durability in case of cold restarts. What a cold restart is something of a catastrophic event. So let's say a lot of operators are failing downstream, and that's resulting in the upstream operators failing. So it's like a cyclic loop. And for some reason, you cannot replay from the checkpointed state. It could be any reason. It could be a Hadoop distribution upgrade. Could be that you've serialized something that has garbled the checkpoints. So in those cases, you have to do a cold restart. What that means is you're losing all of the aggregates that you have because we have an in-memory store. So for the allocation engine, we cannot really afford that. It feeds into our auction engine. So that is catastrophic. So that's why we've sort of moved on to HDHT, which basically means that in any case, we are not losing any of the aggregates that we have. So I could have a live to date aggregate and still retain it, even though I do a cold restart. We have the ability to aggregate and export the data to an external DB. We're using MySQL right now. I believe writing it to another store could be just as seamless. We use it for feedback to critical ad serving components. Yeah. Right, so what were our learnings and challenges along this year and a half journey? So I would say DAG sizing is critical to doing what you are. Identify your use case, size of the DAG. So the way you would proceed typically is that, let's say you just have a dashboard use case, but you need to build out an ingestion operator, ETL operators, aggregations, and an ability to connect a store and an ability to connect the store to your middleware and then the UI, right? So all of these operators, sizing them is critical. Identify your data inflow patterns. So for us, some of our logs arrive at a lesser velocity than some of the other logs. So those operators, we can afford to have fewer instances of them, lesser powered instances in terms of the memory that they consume. So the other thing is that the locality of the operators, something like a Kafka input operator. Yeah? Oh, OK. Something like a Kafka input operator, we have it as a container local operator with the operators that decompress things, because serializing it over multiple containers in the STRAM was consuming a lot of resources. Cardinality estimation for incoming data is critical. For any in-memory store, what happens on a lot of occasions is that you sort of underestimate the explosion of cardinalities that you could have. You may go on adding a lot of dimensions to or a lot of metrics really to your DAG, and then what happens is that the store just becomes full, and if you don't have a right expiration policy in place, those operators are going to be full, and they're just going to explode, and what you have in the end is a DAG that's failing because your operators are running out of memory. Upstream operators tend to require more memory than downstream operators. So this operator, right, Kafka, while it's a very lightweight operator, it takes a lot of memory because it's very likely that the ETL operator fails because of an unhandled exception, serialization errors or something like that. When this guy fails, this STRAM connection fails, stream connection fails, and this guy's memory is sort of hard-pressed until it becomes full, and then this guy fails. So usually we reasonably power this guy so that any failures at this tier or below are handled by buffering that data in memory at this tier. Right. So again, back pressure from downstream failures due to skew in velocity of events and upstream failures. So back pressure is one of the things that you need to be very careful about, which is, you could read at 10,000 events per second using the Kafka input operator, but do you need to, right? Because if you're reading at that rate and one of your downstream operators fails, and you're still pushing 10,000 events from your upstream operators, what's going to happen is a cyclic sort of failure scenario where your upstream is continuously pushing data while your downstream is failing. Downstream is not able to handle data, it's failing again, and then the upstream starts failing. So those are sort of unrecoverable events, and you just have to kill the DAG. It gives you a bad user experience. If the user logs in, your store is not able to serve it any data, then it just looks clumsy. Unifier memory sizing is critical. I would say not just memory sizing for the unifier. Unifier is something that sort of combines the data from different partitions. into a single one, and then it sends it to the downstream operator. A lot of times we noticed that we were giving the wrong memory from an operator's allocation to the unifier, which was resulting in bottlenecks and upstream operators failing as a consequence. I would say besides the unifier memory, even the unifier placement and the partitioning scheme is pretty critical. I'm sure Thomas will cover it in his piece. Think fault tolerance and recovery before you start anything. Think what happens if the DAG fails and you have to do a cold restart. Can you afford to lose an aggregate? Or you cannot. Structure your model around that time. Have a fault tolerant store in place. HDHT is a very good offering in that space now. Yeah. Over to Thomas and Apex architecture.
Yeah. Any questions?
I'd be happy to cover any questions around our implementations.
What was your approach to tuning memory usage for operators or for HDHT or the aggregate you mentioned?
First, recommendation. I didn't get it, sorry.
What was your approach for tuning memory?
All right, yeah. So initially, we just started with, we calculated the number of events we might have to store at any given operator. And then we started off with that point on, let's say the Kafka input operator. I said, OK, let me hold 2 minutes worth of data. What did that translate to? Translated to like 5 gigs. So we started off with that point. And then it's obviously 5 gigs into the number of partitions that we have. So our thumb rule was that of the total Kafka partitions I have, given all my Kafka topics, I will have a fifth of the operators, partitions of the operators, basically. And then I said, OK, I need to hold 5 gigs of in-memory events, and that translated to, I need to hold X amount of minutes of in-memory events. That translated to 5 gigs, and then we just tuned it up and down. Yeah. Sorry. OK, yeah. So go ahead, sir. No, it's OK. I can hear him. Yeah.
How many dimensions are you talking about?
We have, let me talk dimension combinations. So we have 23 dimension combinations as of now for 3 metrics. And some of these are very high cardinality dimensions. Yes?
Yeah, so my question was, you seem to be implying that the ETL operator was very CPU intensive and could not keep up with the pace of the Kafka input operator.
Right.
Could you not increase the partitioning sufficiently so that it could keep up?
Well, yeah. So the thing is, we did increase partitioning sufficiently, but what was happening was the velocity with which the Kafka operators used to pump in data and the number of events that the ETL operator could process, because the ETL is also doing decompression, which just sends your CPU into a spike. So we are doing zlib decompression. It used to combine a lot of CPU cycles, and despite increasing it to a reasonable number, we were not able to sort of mitigate the number of the disparity between the velocity with which events were coming in and the ability for the ETL to handle it. We have a 1-to-1 or a parallel partitioning scheme. That means that if I have like 64 input operators, I had like 64 ETL operators, and we actually had moved to a M cross N scheme, but yeah, for a bunch of reasons we couldn't really keep up. So what we did was we put a fix for back pressure, which is limiting the number of events that could come from Kafka input operators at a given point of time. That sort of matched the number of events that the ETL operator could handle. Then we sort of optimized the ETL operator also to a certain degree. So the disparity was gone.
So I still don't understand why you couldn't increase the number of ETL operators way beyond the number of input operators.
Yeah.
So this was an interesting problem, actually. Can you hear me? Well?
What's that?
Can you hear me?
Yeah.
OK. That was an interesting problem, actually. There was good learning in that exercise. And all these limit-related problems started when Kafka came into the picture, which can push data at a very furious and rapid pace if you consume it at full speed. So what happened here is at that version in the platform, there were several things, several issues of not dealing with limits correctly, which have since been addressed. So for example, one of the issues that was there is that back pressure was not working. So what you expect to happen is when an operator cannot take any more, that it slows down, right? And then back pressure builds to the root operator in the DAG. So that wasn't working. This is actually where we found the issue with PubMatic. Because of the fast consumption, especially at peak time, the operators downstream would be overwhelmed. And as they've said, they would perform CPU-intensive operation and memory-intensive operation. They could definitely not handle everything that Kafka would give at the peak time. So back pressure, correct implementation of back pressure, resource limits, and spooling to disk, it's really the fix. Now, we solved these issues, but they haven't been available. The fixes have not been available at that time. So what was done is instead throttling the input. So putting a limit on how fast the Kafka consumer reads from the broker and slowing the entire game down. There is, of course, a disadvantage to that, right? Because now you're not operating at the maximum speed possible. So back pressure functioning correctly is important. Then the question was, why don't we do shuffle? So to have different partition counts for different operators, you have to do shuffle, right? Shuffle slows you down. Every shuffle is pretty expensive, especially if you have a lot of partitions and a lot of data that goes over the network. So we started, the workaround actually was to do shuffle because we thought that would slow down the game. But that did not work out either because of the same back pressure problem. It's just moving the problem to somewhere else. So I think these problems are out of the way. The optimum performance is parallel partitioning for the application, for PubMatic's application, to do parallel partitioning in the first few operations in the processing, and then do the shuffle when you already have pre-aggregated the data and the cardinality has come, the volume has come down. Then put the expensive shuffle, bring it together because you need a key-based partitioning for the store operator.
Yeah, and just to add one more thing, we actually tried out shuffling. So we wrote a join operator after. So we actually wrote a join operator after the Kafka input operators. The problem was the Kafka clusters that we have in different data centers. So the join operator was reading from A data center, B data center, C data center, and there was a lot of disparity even in the volumes coming in, and like a failure for reading from one of the partitions from any of the data centers would just take that operator down. Now what's happening is while my ETL is shielded, that particular operator is failing, and it's still, sort of putting a lot of pressure on my Kafka inputs anyway. The other thing is throw memory at it, right? You can always do that, but the problem is you don't want your memory footprint to go to a size that doesn't justify your volumes, right? So we could have added 50 of those join operators. Let's say I have 64 Kafka partitions, Kafka input operators. I have 128 of those join operators, and I have 128 of those ETL operators. Fine, it solves the problem, but it just doesn't justify having a memory footprint that wide. Although we did that, and that's a part of the still did not solve the problem, and that's a part of the learning.
Didn't solve your problem really, because you ended up with a large AWS bill, right?
Yeah.
So at that time the application was still running on EMR, and additional memory means additional cost. So wasting resources like that would result in additional cost, and it would be a resource wastage because you consider at peak time is in different regions of the world at different times. So those Kafka clusters would sit idle while the other one is operating at full speed, yet you have to allocate capacity for full speed. That was actually solved by providing a Kafka operator that can consume from multiple clusters. So we enhanced the Kafka operator so that it can read partitions from brokers of all of the clusters. And so that balance out, and pretty much balance the load, right, and have pretty much the same traffic around the clock, almost.
Pretty much, yeah.
Yeah.
And I mean, if you look at a streaming system, right, you want your resources to be utilized in optimal fashion across the day. Otherwise, what you do in a typical batch system, you start a job, your resource utilization peaks up, stop it, does nothing for a while, peaks up. You don't want that. Streaming systems should really have a steady flow of, steady velocity of data being processed across the time. If you over-allocate, however, then your allocation is going to be here, but your consumption is going to be somewhere here, which, again, it's a purpose.
There's also an interesting aspect to what Dave just said. If an operator fails, right, then there is recovery. Recovery needs to happen. Depending on where in the DAG an operator fails, the expense for the recovery goes up. So, for example, recovering the store operator is more expensive because what is happening, since it's using the checkpoint as the place to store the data, this operator is very sensitive to size, to cardinality, because the in-memory state needs to be checkpointed. B, it takes a longer time to bring it up because there's no incremental load. You have to deserialize the state and bring it back into memory. Unlike with HDHT, it's a lazy load, right? You read as you need the data. Failures in the beginning of the DAG would result in a reset of the operators that are partitioned with a shuffle. And expensive operation. All of these issues we found ways to mitigate. It was interesting to walk through them, and it gave us also valuable insights to improve the platform.
Right. Thank you. Any more questions for me? All right. Over to you, Thomas.
Okay. So let's look a bit under the hood. First of all, what is Apex? What are the different components? Apex is everything down here. It starts, of course, we are Hadoop native. We run on top of all the Hadoop distros that are out there. We have a stream processing engine, the runtime, which is Apache Apex now. And from the beginning, we had an open source operator library, which is named Malhar. And Malhar has been a GitHub project now. It's part of Apex. It gives you, so you have an engine. You can write applications against the engine API. Now, starting from scratch is a lot of work. So we also give a library of operators that get you started to build an application quicker. And especially for areas that are generic, like adapters for input and for output, it has implementations that you can use, and it lowers the cost of building an application. So on top of the Apex stack, the Apex platform, DataTorrent has a set of tools as part of the Enterprise Edition, and those are things that make it possible, generally ease development, but also ease operations for a system, and out of the box provide support for data visualization, for example. And this is part of the Enterprise Edition, and Apex is part of it and is offered by DataTorrent. So let's move on. The operator library. So Dave mentioned, yes, please.
REST API, is it part of Apex?
Yes, Apex, the application master in Apex has a REST API. There's another REST API that is part of RTS because there's an additional component, which is, think of it as a management server that runs and can coordinate and support operations across several applications. So, yes?
Yes, we actually use it for monitoring and just to check if the application is running fine, if the end-to-end latencies are within thresholds. We'd actually developed another sort of a monitoring tool on top of it to avoid those cyclic failures that that Thomas mentioned earlier. So it's pretty useful and it's easy to use.
And you're using the console, of course, the UI, to look at the application and to manage it.
Right. Yeah.
Yes. Okay, so then what's in Malhar, what's in the operator library? As I said, adapters for input and output, and also compute operators. some of which Dave has already mentioned. Kafka input-output operator is part of this library. I believe our Kafka input adapter is pretty feature-rich and sophisticated. Thanks also to running it in production for some time and adding useful features to it. We support databases, other message buses, and so on. NoSQL databases and SQL databases. And also for computer operators, the dimension computation operator is actually, at least the framework, is something that originated in Malhar. Now DataTorrent has additional implementations that are part of the enterprise proprietary library that are out of the box working with HDHT, which is PubMatic is using, and similar support. So Hadoop native integration. So Apex was built from the beginning to run on Hadoop. And that brings a few advantages. So the integration is native. That means we can take advantage of the support that the resource manager provides directly. And we also know that we are running in an environment that A has a resource manager and B has a file system. So this says HDFS, but actually it's DFS. It's a implementation of the Hadoop file system. For example, it also works with the MAPP file system. So we are running, or Apex runs on all of the major Hadoop distributions, and including the EMR, where PubMatic's application has been running for a long time before they took it in-house. So let's look a little bit more on the architecture here. Wrong button. So in any Yarn application, you have an application master. And an application master is the brain of the application that knows how to orchestrate the execution. And to run an Apex application, yes, we have an application master, but then the real work is being done by containers that you see here, all the green boxes. And those contain the operators at execution time. So Yarn is the supported execution layer for Apex. And because we are running on Yarn, now what are some of the advantages that we get from that? For example, when there's a failure, when one of those green boxes fails, then we will come to know about it because that's the job of the Yarn cluster. It's the job of the collective job of the node managers and the resource managers to notify of failure. So, but that's it, right? Notification is there. What we do with the notification, that's part of Apex itself, right? That we can recover. It's fully fault tolerant, and that we don't lose any data. All of that is part of the Apex engine and the platform. What it also gives running on Yarn is multi-tenancy. So as you see here, there are some MapReduce boxes in here. They have nothing to do with Apex. Those are just is a proxy for other applications that can run on the cluster under different user IDs, isolated from what is happening in the Apex application in this example. Different users can launch applications. Resource manager gives the ability to configure queues, to enforce different resource limits, and it will also provide security so that one user cannot access things that belong to a different user. And the Hadoop security was originally developed in Yahoo, and that was precisely for the reason that a single infrastructure was used to run applications of different groups. And so it was necessary to add something to Hadoop that wasn't there before, is security for HDFS and for other components so that you have the isolation. And it's Kerberos-based. And if you want to learn more about the security support in Apex, then we have actually something coming up on our blog site soon, and written by Promote, and you can read that, and you will learn how this all works from a security perspective. So what else does Yarn provide us? So you have the resource manager, and when you have a resource manager, then you know what is running on the cluster. So the tools here, the clients, they can connect to the resource manager and find out what applications are running. We talked about the management server, the DT gateway. DT gateway is the component that implements one of the REST APIs. So the other clients can connect to the DT gateway, like PubMatic's custom monitoring tool actually connects to the gateway to find out about the applications that are running. It can access metrics from the application and make decisions based on those metrics. For example, one of the metrics that we implemented was in the Kafka operator to find out from which progress our data is consumed, at which rate, and so on. The DataTorrent UI is a client to the gateway as well. That's a feature-rich console that visualizes many aspects of applications at runtime. Part of Apex is a CLI, command line interface, that lets you perform the same management tasks in a different way. And you can connect to applications that are running on the cluster. You can list operators, you can display statistics, and you get those things in JSON format, so you can also write tools against it. Okay, let's skip forward. How is an application defined? An application is defined as a directed acyclic graph, so it contains operators and edges. The edges are streams, and the operators are the functional building blocks that you use to define your application's logic. As I said, many of these blocks are readily available from Malhar. You can use them. What would typically happen when you build an application, you will have some business logic, and then that business logic needs to be implemented. So typically you also have some custom operators or extensions of operators that are already there. Examples as mentioned in PubMatic. So you define your application in this way. You use smaller units and combine them to achieve a higher goal by connecting them with streams. So a stream is defined as a sequence of data tuples, and an operator can consume one or more streams, then perform computations, and then emit results to one or more outputs. And the resulting logic is a directed acyclic graph. Here's an example. This is the Hello World application of the big data application space. Word count. It's simple and easy to understand. You have an operator that reads lines from a file. Then you have a parser that tokenizes the lines. You count the occurrences of each word, and finally output them somewhere. And this is the corresponding logic written the way you would do defining an application on Apex. So you have the DAG object, you add operators to it, and then finally you connect ports, which is a concept that is unique to Apex platform. 5 minutes? Okay. So let's just skip quickly through and then take some questions. So as Dave indicated, there is quite some support for partitioning and scaling options. There are many dials that let you tweak applications and make it perform. Some of the highlights are unifiers and cascading unifiers. So what you can do, for example, you can combine or take the output of a subset of the partitions into a unifier, and then again combine the result over multiple levels of unifiers. And this obviously is there to support large-scale aggregation. The idea is that in each hop, you shrink the output by aggregation operation, and then at the end you arrive at a manageable output that can be handled by one single operator, which wouldn't be possible if you channeled all of those many partitions into one single operator. For example, the bottleneck could be the network interface. So then different partitioning schemes, parallel partition, which lets you combine multiple operators in parallel pipes that work independent of each other before you introduce things like shuffle, which I mentioned before, makes for a nice high throughput ingest mechanism before you apply aggregations and then bring things together for further processing. And then the M cross N partitioning, we also have some support to do efficient shuffle. And so something that is important in DataTorrent is the concept of a window, a streaming window, and the streaming window is understood by the engine to perform certain operations. So there are data tuples are grouped into windows. Windows are not batches. Windows are actually just markers that are in the stream. And they are passed through the application. They're flowing like all the other tuples, which is important because this is actually a stream processing engine, a pipeline architecture. This is not a batch system where we are waiting for input before we can do something. Every event is moved through the DAG as fast as possible, which allows us to be a low latency architecture. We have been used in use cases where it really matters with low milliseconds. And the support for that comes from the fact that this is a low latency, yet a high scale event-based architecture. So Windows, then there's support for sliding windows, for tumbling windows. Checkpointing is between windows. There's an opportunity to take the state of an operator and write it to durable storage, which allows us to recover to that state on failure. So there's a blog actually about checkpointing. If you're interested in that topic, it's a very important topic when choosing a processing engine. You can read up about that on the DataTorrent website. So some of the things for fault tolerance. So as we said, everything is checkpointed in fault tolerance, application state, application master state. So the controller is not a single point of failure. It's also HA, and there's no data loss. And then another thing, different processing, semantics. So at least once, at most once, exactly once in the true sense of the word, that there is no duplicate processing. And so output to external systems without duplication. Exactly once is different from no data loss. You can have that with at least once too, but you can end up with duplicates. Then data locality optimizations that were also used in PubMatic. You can bring together operators in a single container, avoid the hop over the network, avoid the cost of serialization. You have the ability to even combine operators in a single thread, which can make for very high throughput. If they don't compete for resources, then you can do that, and you get a real boost for your processing. Dynamic updates. We're running out of time, so I'm skipping through. So there are some resources listed here. Visit the Apache Apex community page. Have a look.
Thomas, maybe I can take that.
Yes, Desmond, please take it.
Yeah, so let me come to the front. So my name is Desmond Chan. I'm one of the co-organizers of these meetups. And first of all, thank you so much for coming to the meetup today. We like your physical presence, but we also like your virtual presence. And we're trying to build a community online as well. So just like what Thomas was saying, there's a community page on the incubator web section. So there is a link on our slide that you can go to. We'll distribute these slides after this event. And also there's a LinkedIn group. So please feel free to join all of these. And we don't want to be a one-way push. We don't want to just push the information to you. We also want to hear from you, and we also want to encourage discussions amongst the members. So feel free to join these groups. And also today you signed in. When you signed in, you actually did one of these polls. So we have a few of these names for our mascot. Apache Apex is the technology, but there's an ape there, and we want to name him, or her, actually. So tonight, we've got some preliminary results. Bigfoot is still taking the lead, and just like what we have for the other polls online in the meetup groups. And there is a very surprising result, because we have an other field, and I think there's one company that voted for this name, Ilya. So I think you know who you are. So I have put that on all of the online polls already, and see how the community reacts. If you missed the opportunity to vote tonight, please go on the meetups and just cast your vote there. And other than that, I have the mic. If you want to ask the speakers any questions, please feel free, and then I will just pass you the mic. And Charu, you have anything to add?
No, just I was just trying to take that question.
Yeah. Any questions for the speakers? Don't be shy. I mean, we still have these two great speakers here. Or is there any last words of wisdom for the audience?
So yes, if there are no questions, then I just want to reiterate. So all of the things that you saw, almost all of the things are open source, Apache Apex project. We are in the process of building out our website too, so you find new documentation there and release information. You find information how to get involved. There are email lists there's the email list that is good to subscribe to, and we are welcoming contributors. We are welcoming any feedback also, questions about the use of Apex, ideas where it can be improved, new features, and any sort of feedback. And so yeah, would be nice to see some of you getting involved.
Yes.
I'd like to reiterate that. And finally, just a word of thanks to MAPP, and a very special thanks to Alicia. She's sitting there in the corner. She's the community manager at MAPP, and she's done a fabulous job at helping us and helping. So thank you, Alicia, for all your hard work, and thank you for staying till 7:45 in the evening. But the only silver lining is that the traffic back will be hopefully not so bad for everyone. So thanks, everybody, for being here. Really appreciate it. And we can be around here for some more time if you know you have some one-on-one questions, just want to chit-chat, have some more pizza. There's lots left. Grab another beer if there is. I don't know. But thank you.